Imagine standing in a darkened room, convinced you're alone. Then you feel it, a subtle vibration through the floor, a whisper of movement in the air. Something massive is present, but completely invisible to your eyes. This is precisely the situation humanity finds itself in when we look at the cosmos. Every star we see, every galaxy captured by our most powerful telescopes, every planet and nebula and cosmic wonder, all of it together represents less than 5% of the universe. The rest? It's there. We know it's there, but we cannot see it. What if I told you that woven through the fabric of space, passing through your body at this very moment, is a vast cosmic web of invisible matter, material that doesn't emit light, doesn't absorb light, cannot be touched or measured directly, yet its gravitational fingerprints are everywhere? What if everything we can see is merely the foam on an ocean whose depths we've barely begun to fathom? Today, we journey through evidence that challenges everything we thought we understood about the substance of reality itself. Subscribe to my channel, Relativity Vault. Also, tell me in the comments, which country are you watching this video from, and what time is it there right now? Prepare yourselves, we begin. In 1933, a Swiss astronomer named Fritz Zwicky pointed his telescope at the Coma Cluster, a collection of over 1,000 galaxies located 300 million light-years from Earth. What he observed there would haunt cosmology for the next 9 decades. Zwicky was measuring how fast individual galaxies were moving within the cluster. Using basic Newtonian physics, he could calculate how much mass the cluster needed to hold itself together gravitationally. The math was straightforward. Faster-moving galaxies require more mass to prevent them from flying apart into the void. What he found was impossible. The galaxies in the Coma Cluster were moving so fast, averaging 1,000 kilometers per second, that the visible matter simply couldn't account for the gravitational grip holding them together. By his calculations, there should be 400 times more mass present than what he could see through his telescope. Think about that. Imagine weighing yourself on a scale that reads 400 pounds, but when you look down at your body, you can only account for 1 pound of visible flesh and bone. The other 399 pounds? Somehow present, somehow real, but completely invisible. Zwicky called this invisible mass Dunkel Materia, dark matter. The name was prophetic. For decades, most scientists dismissed his findings as observational error or misunderstanding of galactic dynamics. The idea seemed too radical, too strange. But Zwicky was right. In the 1970s, astronomer Vera Rubin conducted meticulous observations of spiral galaxies, measuring the rotation speeds of stars at various distances from galactic centers. According to everything we understood about gravity and orbital mechanics, stars farther from the galactic core should rotate more slowly, just as Neptune orbits the Sun more slowly than Mercury. That's not what Rubin found. Stars at the outer edges of galaxies were rotating just as fast as stars near the center. Some were even accelerating. the rotation curves were flat, extending far beyond where visible matter ended. These galaxies were behaving as if they were embedded in massive halos of invisible material, spheres of unseen mass extending hundreds of thousands of light years beyond the visible disk. The implications were staggering. Either our understanding of gravity, one of the four fundamental forces, tested and confirmed time and time again, was fundamentally wrong, or the universe contained vast quantities of matter that emitted no light whatsoever. Here's the central mystery. If this dark matter doesn't interact with light, what is it made of? Everything we've ever touched, measured, or observed is composed of atoms, protons, neutrons, electrons. These particles interact electromagnetically. They absorb and emit photons. That's why we can see them. But dark matter appears to interact only through gravity. It has mass. It creates gravitational fields. It shapes the motion of everything around it. But it passes through ordinary matter like a ghost through a wall. The paradox deepens when we consider what this means. At this very moment, you are sitting in a stream of dark matter particles. They're flowing through the Earth, through these walls, through your body, trillions upon trillions of them every second. Yet you feel nothing. No impact, no friction, no interaction whatsoever. It's as if two universes occupy the same space. One universe, ours, is made of atoms, light, chemistry, and life. The other universe is composed of shadow material, invisible and intangible, yet gravitationally dominant. Scientists began asking, if we can't see it or touch it, how do we know it's really there? Could there be another explanation? Physicists proposed modifications to gravity, theories like MOND, modified Newtonian dynamics, that suggested gravity might behave differently on cosmic scales. Perhaps we didn't need invisible matter. Perhaps we just needed new equations. But the evidence forces us to confront an uncomfortable possibility. What if the invisible matter is real? What if the universe we see is merely a luminous skeleton suspended in a vast body of darkness we cannot perceive? The question became urgent. Can we find direct evidence for dark matter's existence beyond these rotation curves and gravitational anomalies? The answer would come from the most violent events in the cosmos. In August 2006, NASA's Chandra X-ray Observatory turned its gaze toward a cosmic collision 3.7 billion light-years away. Two enormous galaxy clusters, each containing hundreds of galaxies, each with a total mass of 1,000 trillion suns, had slammed into each other at speeds exceeding 4 billion kilometers per hour. The collision zone was called the Bullet Cluster. What astronomers observed there provided the most compelling evidence yet for dark matter's physical reality. Here's what they saw. The hot gas clouds from both clusters, visible in X-rays and comprising most of the normal matter, collided and slowed down dramatically, creating a shock wave visible as a bright glow between the clusters. This made perfect sense. Gas clouds interact. They collide, heat up, and lose momentum. But the mass, the gravitational center of each cluster, as measured by gravitational lensing, kept moving. The gravitational effect passed right through the collision site, barely slowing down at all. Think about what this means. The ordinary matter collided and stopped. The dark matter passed right through, like two ghosts intersecting in the night. The separation was clear, measurable, and undeniable.
you could see with your own eyes the spatial offset between where the light-emitting matter was and where the gravitational mass was located. This was the smoking gun. Alternative theories of gravity couldn't explain this. Gravity doesn't separate from the matter creating it unless there's additional matter you cannot see. Scientists discovered similar patterns in other colliding clusters, Max J0025-1222, the Musketball Cluster, Abell 520. Each collision showed the same separation between visible matter and gravitational mass. Each one confirmed that something invisible and massive was passing through collisions unimpeded. But this represents just one piece of a much larger puzzle hidden in the structure of the cosmos itself. In the 1990s and 2000s, massive galaxy surveys like the Sloan Digital Sky Survey began mapping the three-dimensional distribution of galaxies across billions of light-years. What emerged was breathtaking. Galaxies aren't scattered randomly through space. They form a vast cosmic web, filaments and walls of galaxies surrounding enormous voids. This web-like structure spans the observable universe. Filaments stretch for hundreds of millions of light-years. The voids can be 500 million light-years across, nearly empty of galaxies. Computer simulations showed that this exact pattern emerges naturally from the gravitational collapse of dark matter. In the early universe, tiny quantum fluctuations in the dark matter field were amplified by gravity over billions of years. Dark matter collapsed first into filaments and nodes. Then, like dew condensing on a spider's web, ordinary matter fell into these gravitational wells, and galaxies formed where dark matter was densest.
The large-scale structure of the universe is a fossil record of dark matter's existence. We see its architectural blueprint written across the cosmos. The pattern is too precise, too universal to be coincidental. Scientists discovered even more compelling evidence in the cosmic microwave background, the afterglow of the Big Bang itself. This radiation, emitted when the universe was only 380,000 years old, contains subtle temperature fluctuations at the level of 1 part in 100,000. These fluctuations encode the acoustic oscillations of matter and radiation in the infant universe, essentially sound waves rippling through the primordial plasma. By analyzing their precise pattern, cosmologists could determine the exact proportions of different components in the universe. The results were unambiguous. Ordinary atomic matter comprises 4.9% of the universe's total energy content. Dark matter comprises 26.8%. The universe contains more than 5 times more dark matter than ordinary matter. We are the minority constituent of creation. We are the foam on the ocean. What scientists found challenged everything we thought about our place in the cosmos. But the evidence extends beyond gravitational effects into the realm of the very small, into the quantum foam where particles appear and disappear in femtoseconds. Deep underground, shielded from cosmic rays by miles of solid rock, scientists have built some of the most sensitive detectors ever constructed. These experiments have a single purpose: to catch a dark matter particle in the act of interaction. The theory is elegant. If dark matter particles exist and they're passing through Earth constantly, occasionally, perhaps once every few years,
A dark matter particle should collide with an atomic nucleus in the detector. This collision would release a tiny amount of energy, detectable as a faint flash of light or a minute temperature increase. Experiments like Xenon 1T in Italy, Lux ZPL in South Dakota, and Panda X in China use tanks containing tons of ultra-pure xenon or argon, cooled to near absolute zero, monitored by hundreds of sensors. They're waiting for the whisper of dark matter's touch. So far, no confirmed detection. The silence is profound and troubling. But this absence tells us something crucial. If dark matter particles exist, they interact with ordinary matter even more rarely than we thought. The interaction cross-section, the probability of collision, must be extraordinarily small, smaller than physicists initially predicted. This leads to a disturbing possibility. What if dark matter isn't a single type of particle, but an entire dark sector? What if there are multiple species of dark matter particles, perhaps even dark forces binding them together? An entire shadow physics we cannot access. The most remarkable discovery involves hints of unexpected complexity in dark matter's behavior. Recent observations of ultra-faint dwarf galaxies, tiny galaxies orbiting the Milky Way containing only a few thousand stars, reveal something strange. These galaxies seem to have lower dark matter densities at their centers than simulations predict. The cores are less dense, more spread out, as if something is preventing dark matter from collapsing completely. This shouldn't happen if dark matter is truly collisionless, interacting only through gravity. Some physicists now propose that dark matter might have its own weak self-interaction, that dark matter particles might occasionally scatter off each other through an unknown dark force. Think about the implications. There could be dark electromagnetism, dark photons, perhaps even dark chemistry occurring in dense dark matter regions. An entire periodic table of dark elements, completely imperceptible to us, yet gravitationally shaping everything we observe.
At the largest scales, astronomers studying gravitational lensing around massive galaxy clusters have detected anomalies, small-scale distortions in the lensed images that hint at clumps and substructure in the dark matter distribution. These clumps might be ancient dark matter asteroids or planets, formed in the early universe and surviving to the present day. Could there be dark matter structures as complex as planets or stars? Most physicists say no. Without electromagnetism to dissipate energy, dark matter can't cool and condense into such structures. But recent theoretical work suggests loopholes. If dark matter has even weak self-interactions, hierarchical structures might form. We might live in a universe where dark matter galaxies interpenetrate our own, where dark matter planets pass through Earth unnoticed, where an entire parallel cosmology unfolds invisibly around us. The evidence extends beyond our galaxy, into the deep past, into the cosmic dawn when the first stars ignited. Recent observations by the James Webb Space Telescope have detected galaxies forming earlier than predicted, mere hundreds of millions of years after the Big Bang.
These galaxies are more massive and mature than models suggested they should be. The explanation might lie in dark matter. In the early universe, dark matter collapsed first, creating the gravitational wells where ordinary matter could accumulate rapidly. The efficiency of this process determines how quickly galaxies formed. The Webb observations suggest dark matter's influence in the early universe was even more profound than we realized. This forces us to reconsider fundamental assumptions about cosmic evolution. Dark matter wasn't just a passenger in the universe's development, it was the architect, the scaffolding upon which everything else was built. So what is dark matter made of? After decades of observation, theory, and experiment, physicists have developed several compelling candidates. The leading candidate is a class of particles called WIMPs, weakly interacting massive particles. These would be massive, stable particles left over from the Big Bang, interacting only through gravity and the weak nuclear force. WIMPs would have been produced in enormous quantities in the hot early universe, then cooled and dispersed as space expanded. The elegant part: calculations show that particles with weak force interaction strengths naturally produce the correct dark matter abundance we observe today. It's called the WIMP miracle. The physics works out almost too perfectly. But despite decades of searching with increasingly sensitive detectors, we haven't found them. Another compelling candidate: axions. These are ultra-lightweight particles, billions of times lighter than electrons, proposed in the 1970s to solve a different problem in particle physics. If axions exist, they would have been created in such vast quantities in the Big Bang that their collective mass could account for all dark matter, despite each individual axion weighing almost nothing. Think of it like this: WIMPs would be like invisible bowling balls, sparse and massive. Axions would be like an invisible fog, trillions upon trillions of particles creating the same gravitational effect through sheer numbers. Experiments like ADMX at the University of Washington are searching for axions by looking for their predicted conversion into photons in strong magnetic fields. The search is painstaking. Axions could have any mass within a broad range, and each mass value must be checked individually. Then there are more exotic possibilities: primordial black holes formed in the first second after the Big Bang, sterile neutrinos, ghost-like particles that interact even less than ordinary neutrinos. Dark matter might be composite particles, bound states of more fundamental dark constituents. Leading physicists at institutions from CERN to Caltech are exploring all these possibilities. Catherine Fries at the University of Texas has proposed dark stars, hypothetical stars in the early universe powered by dark matter annihilation rather than fusion. Vera Rubin Observatory in Chile, scheduled for full operations soon, will map dark matter distributions across half the sky. What emerges from all this research is a picture of profound complexity. Dark matter isn't just some inert, uniform background. It has structure, dynamics, possibly even its own rich physics. We're not just missing a piece of the puzzle, we're missing an entire parallel picture.
This forces us to reconsider fundamental assumptions about the nature of matter itself. For centuries, we defined matter by its ability to emit and absorb light, to engage in chemistry, to form the bonds that create planets and people. Now we must accept that
normal matter is actually deeply abnormal, a rare, special case in a universe dominated by shadow substance. The quest to understand dark matter is accelerating. In laboratories around the world, new experiments are pushing sensitivity to unprecedented levels. The Lux Zeppelin experiment in South Dakota, with 7 tons of liquid xenon, can detect a nuclear recoil with energy equivalent to a mosquito landing on your arm, if that mosquito were at the quantum level. Super CDMS at Snow Lab in Canada operates at temperatures just millikelvins above absolute zero, where quantum effects allow detection of extraordinarily low energy interactions. In space, upcoming missions will map dark matter's distribution with exquisite precision. The Euclid telescope, launched in 2023, is measuring the shapes and positions of billions of galaxies to create a 3-dimensional map of dark matter across 10 billion years of cosmic history. The Nancy Grace Roman Space Telescope, launching soon, will study dark matter through gravitational lensing on an unprecedented scale. Recent breakthroughs suggest new avenues for detection. Physicists have proposed using quantum sensors, devices that exploit quantum entanglement and superposition, to detect dark matter through subtle distortions in atomic clocks or interference patterns in matter waves. If dark matter consists of ultralight axions, they might form a vast galactic halo that oscillates like a cosmic bell at a specific frequency. The entire dark matter halo might be ringing, and we could detect this through its effect on fundamental constants, causing the fine structure constant or electron mass to oscillate at incredibly subtle levels. Experiments like Abracadabra and Haystack are searching for these cosmic vibrations. What technologies might definitively solve this mystery? Some physicists advocate for a global network of dark matter detectors, allowing coincidence detection across continents. If a dark matter particle scatters in detectors on multiple continents within microseconds, it would eliminate background noise and confirm the signal. Others propose detectors in space, on the moon, or in deep-sea trenches, environments with different background radiation signatures that might reveal dark matter interactions invisible on Earth's surface. There's even discussion of using the sun as a dark matter detector. Dark matter particles passing through the sun should occasionally interact with solar nuclei, accumulating in the solar core over billions of years. These particles might annihilate, producing detectable neutrinos. Experiments like IceCube in Antarctica are searching for this signal. Connect to broader questions about the universe. If dark matter has complex physics, could it form structures capable of complexity? Could there be information processing in dark matter systems? Not life as we know it. That requires chemistry, energy transfer through photons, thermodynamic gradients, but perhaps something we wouldn't recognize, operating on completely different principles. This means for us, we are living in a universe whose true nature remains hidden. Everything we've accomplished, all of science, technology, civilization, has been built from manipulating less than 5% of the cosmos. We're like ancient philosophers who knew only solid Earth, unaware that 70% of Earth's surface is water, or that an atmosphere extends for miles above. What could we achieve if we learned to interact with dark matter? Could we detect it, manipulate it, perhaps even extract energy from it? These questions remain purely speculative, but they hint at technologies and capabilities beyond current imagination. Now we arrive at the most mind-bending implications, questions that push the boundaries of physics and philosophy. The evidence suggests something profound about the nature of reality itself. We are embedded in a universe whose fundamental constituents are hidden from our direct perception. We navigate by the shadows these constituents cast, the gravitational whispers they leave behind. Consider the anthropic implications. If dark matter provides the gravitational scaffolding for galaxy formation, and galaxies are necessary for star formation, and stars are necessary for planet formation, and planets are necessary for life, then our very existence depends on this invisible substrate. Without dark matter, the universe would be radically different. Galaxies might not form at all, or would form so slowly that stars would burn out before planets could develop. The delicate balance that allows for complexity, chemistry, and consciousness relies on the precise amount and properties of dark matter woven through space.
Here's a disturbing thought. What if dark matter isn't uniformly distributed through your body? What if, right now, you contain a higher density of dark matter on one side than the other? The gravitational effect would be negligible. You wouldn't feel anything, but there could be a dark matter asymmetry running through you at this moment. Or, consider this. Dark matter particles have been passing through every human being who has ever lived, through Buddha, Plato, Newton, Einstein, all of them, moved through a constant stream of invisible particles. Every thought you've ever had occurred in a brain permeated by dark matter flowing through the neural tissue. We are, in a sense, always in contact with this cosmic ghost, though we never perceive it. The most profound implications emerge when we consider the possibility of multiple dark sectors, not just one type of dark matter, but families of dark particles, perhaps even entire dark periodic tables. If dark matter has complex interactions among itself, could there be dark matter chemistry occurring in ultra-dense regions? Could dark matter form molecules, crystals, or complex structures through dark forces we cannot observe? Some physicists speculate about dark stars, massive objects composed entirely of dark matter, compressed by gravity but held apart by dark matter self-interactions, emitting no light but potentially detectable through their gravitational effects. These dark stars might be common throughout the universe, invisible cities of shadow matter interpenetrating our cosmos, present multiple possible futures based on the evidence. Future 1. We detect dark matter particles directly in the next decade. We discover they're WIMPs with predictable properties, and we develop theories that explain their creation in the Big Bang and their role in cosmic structure. The mystery is solved, elegant, and complete. Future 2. We never detect dark matter particles because they interact too weakly. Dark matter remains forever beyond our reach, knowable only through gravity. We must accept that the universe contains depths we cannot probe, regardless of how sophisticated our technology becomes. Future 3. We discover dark matter is far more complex than imagined. Multiple particle species, dark forces, perhaps even dark matter structures as intricate as our own. This revelation opens entirely new branches of physics, dark sector science as rich and subtle as quantum mechanics or relativity. Future 4. We find that what we call dark matter is the first hint of extra dimensions, parallel universes, or modifications to physics so profound they reshape our understanding of reality's basic architecture. Which future awaits us remains uncertain,
But the journey toward it continues, accelerating, drawing us deeper into mystery. We began this journey with a simple observation. Galaxies spin too fast for the matter we can see. From that single anomaly, we've uncovered evidence of a shadow universe, invisible, intangible, yet gravitationally dominant, woven through every cubic centimeter of space. We've seen how dark matter shapes cosmic structure, how it passes through itself in colliding galaxy clusters, how its presence is encoded in the cosmic microwave background and written across the distribution of galaxies spanning billions of light years. We've explored the leading candidates for what it might be: WIMPs, axions, primordial black holes, and the ingenious experiments scientists have designed to catch this cosmic ghost in the act of interaction. What have we learned? That the visible universe is merely a luminous skeleton suspended in a vast body of darkness, that matter as we understand it, atoms, molecules, chemistry, life, represents a tiny fraction of the cosmos, that we navigate a reality whose true nature remains largely hidden, like sailors on a dark ocean who see only the phosphorescent foam on the surface, unaware of the fathomless depths below. What remains unknown exceeds what we've discovered. We don't know what dark matter is made of. We don't know if it has complex physics of its own. We don't know if it will forever remain beyond our ability to detect directly. We don't know what technologies might emerge if we learn to interact with it. The current scientific consensus: dark matter exists. It's fundamental to cosmic structure, and its nature ranks among the deepest mysteries in physics. Solving it will require new ideas, new experiments, new ways of thinking about matter and interaction. But here's what makes this mystery magnificent. Dark matter reminds us that the universe is far stranger, far more subtle than our everyday experience suggests. It humbles us, showing us that our perception captures only a sliver of reality. And it inspires us, because every great mystery solved reveals new mysteries beyond. At this very moment, dark matter flows through you, through the earth, through everything you know, invisible, intangible, yet shaping the destiny of galaxies. You are part of a cosmos far grander and more mysterious than you can perceive.
Cinematic and ultra-realistic space documentary use slow, soothing, and atmospheric visuals designed for sleep-friendly content. Include soft lighting, smooth camera movement, deep cosmic colors, and highly detailed textures. The mood should be peaceful, educational, and immersive, like a premium NASA documentary. Ensure every scene feels calm and visually balanced with gentle transitions. The journey doesn't end with acknowledging dark matter's existence. That's merely the beginning, because once you accept that 95% of the universe is invisible, you must confront an even more disturbing question. What else are we missing? In the previous hour, we explored dark matter, the 27% of the universe composed of mysterious particles that interact only through gravity. But there's something even stranger lurking in the equations of cosmology. Something that doesn't just hide from our telescopes, it actively pushes the universe apart. Scientists call it dark energy, and it comprises 68% of everything that exists. Think about what this means. Dark matter we cannot see, dark energy we cannot understand. Together they account for 95% of the cosmic energy budget. Everything we've ever observed, measured, or touched, every star, planet, atom, and photon, represents less than 5% of reality. We are living in a universe that is almost entirely incomprehensible to us.
The story begins in 1998. Two independent teams of astronomers, the Supernova Cosmology Project and the High Z Supernova Search Team, were measuring distances to Type A supernovae in remote galaxies. These stellar explosions serve as cosmic mile markers, allowing astronomers to calculate how fast the universe is expanding at different epochs in its history. Everyone expected the same result. The universe's expansion should be slowing down. After the Big Bang flung everything outward, gravity should be gradually pulling everything back together, decelerating the expansion over billions of years. What they discovered inverted our understanding of cosmic destiny. The universe isn't slowing down, it's speeding up. The expansion rate is accelerating and has been for the past 6 billion years. Imagine throwing a ball into the air and watching it accelerate upward, moving faster and faster as it rises, defying gravity. That's what the universe is doing on the largest scales. Something is overpowering gravity itself. Something is driving galaxies apart with ever-increasing force. The acceleration is subtle, increasing the expansion rate by about 7 kilometers per second per megaparsec every billion years, but its cumulative effect reshapes the cosmos. Saul Perlmutter, Brian Schmidt, and Adam Rees shared the 2011 Nobel Prize in Physics for this discovery. But their prize came with a profound problem. What is causing the acceleration? The simplest explanation invokes Einstein's greatest blunder, or what he called his greatest blunder. In 1917, Einstein added a cosmological constant to his field equations of general relativity. This constant, denoted by the Greek letter lambda, represented a kind of anti-gravity inherent to space itself. Einstein introduced it to keep the universe static, then abandoned it when Hubble discovered cosmic expansion. But the supernova data brought lambda back from the dead. If space itself possesses intrinsic energy, what physicists call vacuum energy or dark energy, then as the universe expands and creates more space, it creates more of this energy. Unlike matter or radiation, which becomes diluted as space expands, dark energy maintains constant density. More space equals more dark energy equals stronger repulsive force. It's as if the vacuum of space is a coiled spring, and the more you stretch it, the harder it pushes back. But here's where it gets strange. When physicists calculate how much vacuum energy quantum field theory predicts, they get a number that's 10 to the 120th times larger than what we observe. That's 1 followed by 120 zeros, the worst prediction in the history of physics. This is called the cosmological constant problem, and it represents one of the deepest mysteries in theoretical physics. Why is dark energy's density so incredibly small compared to theoretical predictions, yet still large enough to dominate the universe? Some physicists propose that dark energy isn't constant at all. Maybe it's a dynamic field, dubbed quintessence, after the fifth element of ancient philosophy, that evolves over cosmic time. Quintessence would be a new kind of energy field permeating space, its density changing as the universe ages. If quintessence exists and strengthens over time, the universe's expansion could accelerate catastrophically. In 50 billion years, galaxies beyond our local group would recede faster than light, disappearing beyond a cosmic event horizon. In 100 billion years, even stars within distant galaxies would be ripped apart. Eventually, atoms themselves would be torn asunder. Physicists call this the Big Rip. Alternatively, if dark energy weakens or reverses, the universe's expansion could halt and reverse, culminating in the Big Crunch, everything collapsing back into a cosmic singularity. Or perhaps dark energy remains constant and the universe expands forever, cooling into a dark, empty void in 10 to the 100 years, the heat death of the universe. Recent observations by the Dark Energy Survey and the Planck satellite have measured dark energy's properties with unprecedented precision. The equation of state parameter, which describes how dark energy's pressure relates to its density, appears to be -1, exactly matching a cosmological constant. But subtle anomalies persist. Some measurements suggest dark energy might be slightly evolving. Galaxy cluster counts don't quite match predictions. The Hubble constant, the current expansion rate, varies depending on how you measure it, a discrepancy called the Hubble tension. Either our measurements contain systematic errors, or something fundamental in our cosmological model is wrong. The evidence forces us to confront an uncomfortable possibility. We might be missing something even bigger than dark matter and dark energy, some hidden variable in the cosmic equations that, deep in the mathematical structure of quantum mechanics, lies a phenomenon that Einstein called spooky action at a distance, quantum entanglement. When two particles become entangled, measuring one instantly affects the other, regardless of the distance separating them. This isn't just theoretical. Physicists have demonstrated quantum entanglement across hundreds of kilometers. China's MOSIUS satellite achieved entanglement between ground stations 1,200 kilometers apart. The effect is real, verified, and deeply strange. But here's what most people don't realize. Quantum entanglement might not be limited to laboratory experiments or satellite communications. It might be woven into the very structure of space-time itself. In 2013, physicists Juan Meldacena and Leonard Susskind proposed a radical idea. Quantum entanglement and wormholes, shortcuts through space-time, might be two descriptions of the same phenomenon. They called it ER equals EPR, connecting Einstein-Rosen bridges, wormholes, with Einstein-Podolsky-Rosen entanglement. If true, every pair of entangled particles is connected by a microscopic wormhole at the quantum scale. Space itself might be stitched together by countless quantum threads of entanglement. The fabric of space-time could be an emergent property arising from quantum entanglement of more fundamental entities. This suggests something profound. Space and time might not be fundamental features of reality. They might be constructed from something deeper, quantum information encoded in patterns of entanglement. Recent theoretical work by physicists, including Mark van Ramsdam and Brian Swingle, have developed this idea further. They've shown that the geometry of space-time in certain theoretical models emerges directly from the entanglement structure of quantum fields. In these models, if you increase entanglement between regions, you make those regions closer in the emergent space-time. If you decrease entanglement, you make them farther apart. Distance itself becomes a measure of quantum information. What does this have to do with dark matter and dark energy? Consider this. If space-time geometry emerges from quantum entanglement and dark matter affects space-time geometry through gravity, then dark matter might be affecting the underlying entanglement structure of reality. Dark matter could be regions of space-time with altered quantum information content.
Even more radical. What if dark energy represents the baseline quantum entanglement of empty space? The cosmological constant could be the ground state
entanglement entropy of space-time itself, a measure of how much quantum information is woven into the vacuum. This would explain why dark energy is so difficult to calculate. We're not calculating the energy of particles or fields. We're trying to compute the informational content of space-time geometry itself, something far more fundamental than ordinary physics. These ideas remain highly speculative, but they hint at deep connections between quantum mechanics, gravity, and the dark sector that we're only beginning to glimpse. The most disturbing evidence comes from attempts to unite quantum mechanics and general relativity, the quest for quantum gravity. In 1974, Stephen Hawking calculated that black holes aren't entirely black. Due to quantum effects near the event horizon, they emit thermal radiation, now called Hawking radiation. This means black holes slowly evaporate, losing mass and eventually disappearing completely. This created a paradox. Black holes destroy information. Everything that falls in, every particle, every bit of quantum information seems to be erased when the black hole evaporates. But quantum mechanics says information cannot be destroyed. It's a fundamental principle called unitarity. For decades, physicists debated, does information fall into black holes and disappear, violating quantum mechanics? Or does it somehow escape, violating general relativity? The resolution appears to involve quantum entanglement in ways that blur the boundary between inside and outside the black hole. Recent calculations suggest that information isn't lost. It's encoded in subtle correlations in the Hawking radiation through quantum entanglement. But retrieving that information would require measuring the entanglement between trillions upon trillions of particles emitted over billions of years. It's preserved in principle, but irretrievable in practice. Here's where it connects to the dark sector. If information is preserved through quantum entanglement and dark matter interacts gravitationally, then dark matter falling into black holes must also have its information preserved somehow. But dark matter particles don't interact electromagnetically. They don't emit light or participate in any process we can measure except gravity. So how is their quantum information encoded in Hawking radiation? Some physicists propose that dark matter might have its own dark Hawking radiation, emitted through dark sector interactions that carries away information through dark channels we cannot observe. Black holes might be portals connecting the visible universe and the dark sector, with information flowing between them through mechanisms we don't yet understand. Even more provocatively, what if the information paradox is telling us that reality at its deepest level isn't divided into particles and fields at all? What if the fundamental nature of reality is pure quantum information and particles, both ordinary and dark, are merely how that information manifests when viewed from our particular perspective? In this view, dark matter isn't made of unknown particles. It's a different informational structure in the quantum grammar of reality. Information encoded in ways that manifest as gravitational effects, but not electromagnetic ones. This would make dark matter less like an exotic substance and more like an exotic encoding, a different alphabet in the quantum grammar of reality. The evidence extends beyond black holes into the structure of the universe at the smallest possible scales, the Planck scale, where space-time itself becomes quantum and grainy. At this scale, 10 billion trillion times smaller than an atomic nucleus, our concepts of space and time break down completely. And that's where our journey must now descend, into the quantum foam, where reality itself fluctuates.
We've established that the universe contains vast amounts of invisible matter and energy. We've explored how space-time might emerge from quantum information. Now we must confront an idea that seems like science fiction, but arises from serious physics and philosophy. What if the universe is computational in nature? Not a computer simulation created by some external programmer, but something deeper. What if the universe is a kind of information processing system, and physical laws are the algorithms it runs? This idea has respectable roots. Physicist John Wheeler, who coined the terms black hole and wormhole, proposed a principle he called it from bit, the idea that every physical quantity derives from binary information. Reality emerges from yes or no questions, from bits of information. More recently, physicists have noted that the universe appears to have computational limits. There's a maximum amount of information that can be stored in any region of space, defined by the holographic principle. There's a maximum speed for information propagation, the speed of light. There are minimum units of space and time, the Planck length and Planck time. These look suspiciously like resolution limits, frame rates, and processing speeds. Seth Lloyd at MIT calculated that the observable universe, treated as a quantum computer, has performed about 10 to the 120 operations since the Big Bang. That's the computational history of everything, every particle interaction, every quantum fluctuation, every thought you've ever had. If the universe is computational, dark matter and dark energy take on new significance. They might represent information that's encrypted or stored in ways our observer frame cannot access directly. Imagine a computer displaying a 3D video game. The graphics you see, the rendered environment, represent only a tiny fraction of the data the computer is processing. Most of the computational activity happens in memory, in background processes, in calculations that never directly appear on screen. What if visible matter is the rendered portion of reality, while dark matter and dark energy represent the bulk of the universe's informational processing occurring in substrate layers we don't perceive? Computer scientist Konrad Zuse proposed in the 1960s that the universe might literally be a cellular automaton, a grid of cells updating according to simple rules, like Conway's game of life, but in 3 dimensions. Stephen Wolfram has developed this idea extensively, suggesting that all physical laws might emerge from simple computational rules operating on a network of abstract elements. If true, particles aren't fundamental. Space-time isn't fundamental. What's fundamental is the computational network and the rules it follows. Everything else, matter, energy, forces, even the distinction between visible and dark sectors,
emerges from computation. This would explain why mathematics describes physics so precisely. Mathematical structures and computational structures are essentially the same thing. The implications are staggering. If reality is computational, then consciousness might be a particular type of information processing pattern arising within the universal computation. You would be a localized information process within a larger informational substrate, a pattern of organization in the cosmic computation. What evidence might support a computational universe? Surprisingly, several observations hint in this direction. First, quantum mechanics is fundamentally discrete. Quantum systems exist in discrete states with discrete energy levels. When you measure quantum properties, you get discrete outcomes: spin up or spin down, particle here or particle there. This is exactly what you'd expect if reality is digital rather than analog. Second, the holographic principle discovered through black hole thermodynamics suggests that the information content of any region is proportional to its surface area, not its volume. This is precisely how holograms work, encoding 3D information on 2D surfaces. It's also how compression algorithms work in computation.
Third, relativity imposes absolute limits on information transfer. Nothing can signal faster than light. This looks like a bandwidth limit, the maximum rate at which information can propagate through the cosmic network. Fourth, quantum entanglement connects distant particles through what appears to be a hidden information channel. In computational terms, entangled particles might share pointers to the same memory location in the universe's substrate. Fifth, the simulation hypothesis, proposed by philosopher Nick Bostrom, argues that if civilizations eventually develop the ability to run detailed simulations of conscious beings, and if they run many such simulations, then statistically we are more likely to be inside a simulation than in base reality. But here's the twist. Even if we're not in a simulation created by another civilization, we might still be in something computational. The universe itself might be the computation, not running on some external hardware, but self-computing. A self-organizing information structure that processes itself into existence moment by moment. This resolves certain philosophical problems. We don't need to ask, what is the universe made of? Because matter isn't fundamental. We don't need to ask, what existed before the Big Bang? Because time is an emergent property of the computation, not a container it runs within. Dark matter and dark energy become less mysterious in this framework. There are aspects of the cosmic computation that don't manifest in the electromagnetic channel we observe. They're background processes, memory management, structural overhead in the universe's information processing architecture. Recent work by physicists, including Chiara Marletto at Oxford, explores constructor theory, a framework that describes physical systems in terms of which transformations are possible, rather than which trajectories particles follow. This is fundamentally computational thinking applied to physics. If this perspective is correct, the quest to understand dark matter isn't about finding exotic particles. It's about decoding the informational structure of reality, understanding how the universe computes itself into existence, and what portions of that computation manifest as observable matter versus dark matter versus space-time geometry itself. The evidence leads us to a radical conclusion. Reality might be information all the way down. We've journeyed from invisible matter through quantum information to the computational nature of reality. Now we arrive at perhaps the most mind-bending possibility. What if dark matter is evidence of parallel universes? This isn't mere speculation. It emerges from taking quantum mechanics seriously, more seriously than most physicists are comfortable with. In 1957, physicist Hugh Everett proposed the many worlds interpretation of quantum mechanics. According to Everett, every quantum measurement doesn't collapse the wave function into one outcome. Instead, the universe splits into multiple branches, one for each possible outcome. All possibilities happen, each in its own parallel world. When you measure a quantum particle's spin, the universe branches into one world where you measured spin up and another where you measured spin down. Both versions of you exist, both experiencing a definite outcome, unaware of each other. If true, and many physicists take this interpretation seriously, then quantum mechanics implies a vast multiverse. Every quantum interaction generates new branches. The number of parallel worlds grows exponentially with each passing moment. But here's the connection to dark matter. In the many worlds interpretation, the other branches don't completely disappear. They exist in quantum superposition with our branch. The mathematics describes them as real, physically present components of the universal wave function. Could those other branches have gravitational effects on our branch? Standard quantum mechanics says no. The branches are completely separate, unable to influence each other except through quantum interference effects. But some physicists have explored modifications to quantum mechanics where branches can have weak gravitational coupling. If parallel worlds exert gravity across branch boundaries, they would appear as invisible mass in our universe. We would see their gravitational effects, but not their electromagnetic radiation, because that radiation exists in another branch. Dark matter could be ordinary matter in parallel quantum branches, gravitationally reaching across the many-world superposition.
This would explain several puzzles. Dark matter appears to have roughly the same distribution as visible matter. It clusters in galaxies, forms halos around them, follows similar large-scale structure. This is odd if dark matter is exotic particles with completely different properties from ordinary matter. But if dark matter is ordinary matter in parallel branches, the similarity makes perfect sense. It would also explain why we haven't detected dark matter particles. We're not looking for particles in our branch. We're seeing the gravitational shadow of matter in adjacent quantum branches. The most remarkable discovery involves recent theoretical work on quantum gravity and the multiverse. Physicists exploring models of eternal inflation, where the Big Bang is a local event in an eternally inflating megaverse, find that different regions of the multiverse can have different physical constants and laws. Eternal inflation theory suggests our observable universe is a single bubble in an infinite foam of bubble universes. Each bubble nucleates from the inflating field, creating a Big Bang event and a region where inflation stops and normal expansion begins. These bubble universes might have different values for fundamental constants, different strengths for the electromagnetic force, different masses for electrons and quarks, different amounts of dark matter and dark energy. Most bubbles would be sterile, unable to form stars, planets, or life, but across infinite space and infinite time, all possibilities occur.
somewhere in the multiverse, every possible physics exists. We find ourselves in a bubble with properties that allow complex chemistry and life, not because our bubble is special, but because only bubbles like ours can contain observers wondering why their universe has life-permitting properties. This is the anthropic principle taken to its ultimate conclusion. Dark matter and dark energy might be finely tuned by anthropic selection. If dark matter were much more abundant, it would have over-collapsed the universe before stars could form. If dark energy were slightly stronger, it would have torn apart atoms before life evolved. We observe the values we do because those are the values compatible with our existence as observers. But this leads to a profound question. If other bubble universes exist with different physics, could they overlap with ours? Could their matter interact gravitationally across bubble boundaries? Some models of eternal inflation suggest yes. Bubble collisions might occur, leaving detectable imprints in the cosmic microwave background, bruises on the sky where our universe collided with another. Cosmologists have searched for such signatures. Several anomalies in the CMB, including the cold spot, a region colder than surrounding areas, could potentially be explained by collisions with other universes. The evidence remains ambiguous, tantalizing but not conclusive. If other universes do interact with ours gravitationally, they would appear as, you guessed it, dark matter. Invisible, intangible, detectable only through gravity. The most profound implications emerge when we combine all these ideas: quantum entanglement creating spacetime, information as the basis of reality, computational universe running probabilistic algorithms, many worlds branching, and eternal inflation generating infinite bubble universes. We arrive at a vision of reality that is simultaneously larger and stranger than anything our ancestors imagined. A reality where space and time emerge from quantum information. Physical laws are computational processes. Quantum mechanics splits the universe into parallel branches. Our universe is one bubble in an infinite multiverse. Dark matter represents information or matter from adjacent realities. Dark energy is the computational overhead of space-time itself. Consciousness is a localized information processing pattern in the universal computation. This isn't mysticism or fantasy. Every element emerges from serious physics and mathematics. It's what happens when we follow the evidence wherever it leads, even when it leads to conclusions that defy intuition. We stand at a threshold. Behind us lies the comfortable universe of stars and planets, atoms and molecules, the 5% we can see and touch. Ahead lies something vaster, a multiverse of quantum possibilities, computational substrates, informational patterns, and parallel realities. Dark matter was our first clue that the visible universe represents only a fraction of what exists. It opened a door. Beyond that door lie infinite further doors, each opening onto vistas stranger than the last. The universe is not just vast, it is incomprehensibly vast, structured in ways that exceed our current conceptual frameworks. We are pattern recognition systems embedded in an information processing cosmos, attempting to decode the source code of reality itself. And we've barely begun.